Hello, everyone, and welcome to today's webinar, Balancing Range and Occupant Thermal Comfort for Mass Transit Applications. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenters today are Marek Lehacki and John Yuskevich. Marek received his Master's of Science in Mechanical Engineering from Czech Technical University in Prague and began his career as a heat exchanger design and quality engineer at Cahan Thermal Technology in 2011. He joined Gamma Technologies in 2013 as a two-phase systems technical consultant and has been the product manager for two-phase and cabin applications since 2019. John is a thermal and CFD engineer at Thermal Analytics and has been a dynamic part of the engineering team since 2013. He received his bachelor's degrees in mechanical and biomedical engineering from Michigan Technological University and completed his master's of science in mechanical engineering from Oakland University. John's current research focus is on the development of transient thermal simulation methods for vehicle packaging studies. Throughout today's presentation, you may submit questions in the questions box and we will review them at the end. We are also recording this webinar and we'll be sending you the link following this presentation. With that, John, if you're ready, you may begin.
Thanks for the introduction, Chris. So as Chris already mentioned, the title of today's webinar is Balancing Range and Occupant Thermal Comfort for Mass Transit Applications. In terms of the specifics of what we'll be talking about today, we're going to start by introducing a little bit of background, talk about the importance of reducing CO2 emissions, balancing range and cabin conditioning, and then how that applies specifically to buses. Then I'll hand things over to Marek and he can describe the integrated system modeling approaches, different approaches for cabin systems modeling, integrating the modeling workflow, and then he'll hand it back to me to talk about different environmental metrics and ways we can rate the cabin. I'll talk about some integrated modeling results and then talk about balancing the energy and occupant perception, and finally some conclusions. And at the end, we'll leave some time for questions. So it's probably not a surprise to anyone in the audience that global temperatures are on the rise and greenhouse gas emissions are attributed to that rise. On the right, you can see the current trend focusing on 2017 and then moving forward. By the time we get to 2040, we're projected to have a 1.5 degree global temperature average rise. Since that's going to be a major problem for many locations and many industries around the world, reduction and mitigation strategies are currently being aggressively pursued in all sectors. On the bottom right, you can see in blue the current trend, and then in gray is the reduction of coal power, and then in green is the CO2 emissions based on the climate accord or Paris Climate Accord. What you'll notice is that over the next few years, we're expected to see extremely dramatic changes in the amount of carbon emissions. The hope is that by reducing that, we can help slow down the global warming trend. And electric buses are just one part of that solution. Here you can see a plot showing the carbon emissions from a diesel bus shown in blue. You'll notice that there's a fairly linear trend, which assumes a constant usage over the 12-year life cycle of the bus. Compare that to the green and the red lines, which are two different battery-powered buses that have significantly lower carbon emissions, even when you factor in replacing the battery at the 6-year mark halfway through the product life cycle. So clearly, moving to electric buses is one way we can potentially influence this trend and help get to a reduced carbon environment. To complicate that, there's a strong weather factor when thinking about electric vehicles. If you think about consumer vehicles, based on 2013 data, about 35% of vehicle ranges or energy is used in the winter and about 25% in the summer. Then this directly affects the vehicle range. You can see that on the plot on the right-hand side, which compares the available range in miles on the y-axis, and then on the x-axis, the ambient temperature. You'll notice that the peak vehicle range is in a fairly narrow band, and this is confirmed at the lower plot based on the energy system requirements, looking at a number of different drive cycles and different ambient conditions. The important thing to remember here is that a great deal of the energy in the vehicle is going towards things that aren't necessarily extending the range, things like cabin conditioning. Electric buses have very similar issues, and because of that, they're a challenge to design. But despite that, many municipalities are still seeing that electric buses are critical for the future of urban mobility. And you can see several examples of that on the right. Fully electric buses have a significant problem in that there's no waste heat available to condition the cabin with. And in an area like Western Europe, where you're going to need heating capability 60 to 70% of the time, that becomes a very significant factor, especially when you consider that the HVAC consumption can be up to 60% of the total battery capacity. And if we're using that battery capacity to condition the cabin, where that extra energy or that used energy is retracting from the vehicle range. In addition to that, the buses offer many unique challenges that you don't find in consumer vehicles. Some of those, to name just a few, are the multiple occupants spread out over a very large area. We have varying times on the bus. You can imagine some riders will get on, go 1 or 2 stops and then get off. Others will get on and go 10, 12 stops. So a very different time span that they're in the vehicle. And things like the doors opening and closing. When you have the doors that open at a stop, you're letting unconditioned air into the cabin and increasing the energy requirements. In addition to that, there are things like the many different height and weight percentiles of occupants on the bus, the different clothing ensembles, and many other factors that make this a much more complicated problem.
So thanks, John, for introducing the problem. I will now take over and try to dive a little deeper into how simulation can actually help dealing with the challenges the design engineers may be facing here. So obviously, similar as for the passenger cars, we are standing in front of the trade-off between the passenger comfort when we concentrate on the winter case, just having to decide if we want to keep the bus warm or rather be able to drive the bus a little further. But besides that, we also need to make sure all the components are actually running in some optimal conditions, because that well, not making sure it is the case may cause the components to get damaged, and yeah, this will in the end increase the cost significantly. Historically, the development of the buses has relied heavily on testing, but nowadays, when also in this area, the development cycles are shortening. The number of different possibilities that needs to be tested is increasing. The tests are just yeah, starting to be running on the edge of the possibilities there, and that's where hopefully the system simulation may work, or may help replacing some part of that. If you imagine, for example, having to decide what supplier to be chosen for a rooftop unit of the bus or a battery system, having to test this means that you would have to completely rebuild the vehicle more or less, and then send it into the climate chamber once again, which may take multiple days or maybe even more. And that's not even starting talking about testing of comfort, where you would have to actually have some passengers inside of the bus during the test, and that for multiple times. So all of that is possible within a very short time when a simulation model of this is available, and that very early in the development process, so you don't have to have all the components as hardware available. You just need the information of their physical behavior, and you can set up the integrated system model and get realistic results out of that. What is important here, and what is increasingly important for the electric vehicles and electric buses, is that it's not anymore enough to just test the separate systems, like, for example, the powertrain cooling not connected to the HVAC systems, because nowadays those are very tightly connected. Sometimes, for example, the HVAC system providing the cooling for the battery. So that's why an integrated system is necessary, just to make sure not to miss any parts of the important physics that will in the end affect the driving range of the vehicle, but also, for example, the thermal comfort. So since we are concentrating on the comfort, let's talk about the cabin simulations right now. The tricky part in general for the system simulation is to find the good balance between the simulation speed and the results accuracy and the results fidelity. You can imagine having all the systems starting with the battery chemistry through the cooling loop to the HVAC running on some 3D CFD code. This will probably give quite accurate results, but the simulation times will probably not really be acceptable, and maybe even longer than having to set up and run a test. So this is not really possible here. That's why we are kind of looking for some possibilities to improve the simulation runtime while keeping the fidelity of the system where it is necessary high enough to get the reasonable results. In our case, for the cabin, you can see kind of the standard set of modeling types. We have let's say single or multi-zone cabin models, very fast running, but yeah, a little less accurate on one side, and on the other, the CFD simulation, maybe including the conjugated heat transfer, which of course is kind of the state of the art with the in terms of accuracy, but in terms of runtimes, maybe restrictively slow. And that's why we will try to present some kind of middle solution that we have in the past used also for the passenger cars, that should kind of use the best of both of those two sides, having finally resolved 3D simulation within a reasonable simulation time. So I've mentioned we have been using this on the passenger vehicles examples, and it's not only that Gamma Technologies and Thermoanalytics did this internally. We also have several customers actually applying this solution. Here, just two of them, the tests that were running by Toyota and the test we were doing together with Volvo. Just yeah, to demonstrate the possibilities of the accuracy of such solution compared to the actual test data. And I hope this is kind of showing that the solution is valid, and now we would like to show you how it can be extended for the usage of some larger cabins. So how this methodology works, how do we achieve having a 3D resolved simulation running transient both on the thermal and the flow side, while simulating actually faster than what the 3D CFD would achieve. What we are doing here is that we can use the 3D CFD tools without any details of the thermal structure simulation to predefine a set of flow fields, so a set of CFD results that would resolve the flow inside of the bus cabin for maybe different conditions, like different vent operations or different blower speeds. this solution then can be taken and applied as kind of fixed for different amounts of time to the GT-SUITE flow solution, where the rest, what needs to be solved is the fluid temperature and possibly some species propagation. And on the thermal structure side, we are using the fast TAITherm solver to get the results for the structure temperatures, but also for the passenger comfort and sensation. The recent addition to this, let's say, set of tools has been the GT Converge, which is a CFD tool that in GT-SUITE we have used for quite a while for simulating, for example, the intake manifolds of the engine. But the colleagues at Convergent Science have improved and extended the solution so that now we can use it also for the cabin simulation. This is now seamlessly integrated within the process of the coupling of GT-SUITE and TAITherm, and allows, for example, mostly automatized generation of the CFD data for the later usage in this fast-running coupled simulation. Now let's take a look at how our test case looks like that we would like to present here. So we do have a relatively simple model here available that includes some of the important parts of the system. So we have the cabin of the bus. In this case, it's kind of this short city bus here in the bottom. We do have the air distribution system here just above that, and we have a heat pump system or maybe some conventional air conditioning system attached to it that will just provide the cold air for the bus. How that connects to the coupling solution between GT and TAITherm. The air and the cabin structure temperatures are resolved in 3D within this domain. So we do have the CFD data, in this case generated by GT Converge, used to resolve the airflow inside of the cabin. We do calculate the air temperatures just depending on the inlet air temperatures and on the heat exchange with the structure. And on the other hand, we do have the TAITherm model that allows highly accurate and fast-running thermal wall simulation. So this allows you, for example, to test the different sets of the wall structure, different types of insulations, or maybe different types of glazing in the bus. On the external side, to save some time, the flow around the bus doesn't always have to be resolved by maybe a 3D manners. There are correlations available that can be applied on the exterior and that allow for realistic A/B comparisons. But also the external flow data, if available, can be used here to improve the accuracy and to improve the local temperature resolution. And on top of that, the TAITherm provides tools for simulating the thermal comfort of the actual passengers in there. So you can add the thermal models into the cabin and as an outcome of the simulation, see what comfort and sensation the passengers would feel inside. On the 1D system side, we have the heat pump system that can be flexibly switched within the simulation tool. So you can test different system topologies, different systems from different suppliers, for example, or even systems using different refrigerants that may be the kind of legislatively legislatively constrained usage of R134A, some of the new options for refrigerants like CO2 or R260. So all of this can be actually included in a single model. Within that given topology, you can also switch different components. So for example, select the right supplier for your compressor or the heat exchangers. On the side of the cabin, we are flexible as well. So it doesn't really matter which kind of geometry you choose to simulate. You can switch the geometries within a single model and simulate in one run, for example, a standard city bus, as I have shown it before, maybe an articulated bus, or maybe a travel bus or a coach in a different simulation. Now, quickly to the description of the test case that we would like to show here. I have already shown the layout of the system. So we will be using a compact CO2 heat pump here that is not reversing. We will use some flow flaps to guide the flow through. Here in this case, the gas cooler and the evaporator, depending on the heating or cooling case. And we would like to test what energy consumption this system has depending of the style of heating of the air. So we can either use a PTC heater directly on the air inlet of the cabin, or we can use some localized heaters inside of the cabin, maybe in the region where the passengers would be sitting. We are running this on or starting with a -10 degrees C ambient temperature, and John will then describe us or show us how those two types of systems perform.
All right, thanks, Mark. So we'll start by first talking about what some of the environmental metrics that we can get out of the model. The first one I'll talk about is the equivalent homogeneous temperature, which is a function of the mean radiant and the ambient temperature. And what this does is provides a metric for environmental conditions based on the human perception. It's frequently used as a design target as either a supplement to or a replacement for a standard air temperature. And it can be related to occupant sensation, which is a feeling of warm or cold. What you'll notice in this simulation is that if we look at the driver, they're seeing the highest equivalent homogeneous temperature, reaching a steady value of about 23 C. And this makes sense given that this can be interpreted as being fairly comfortable, since we intuitively know that a room temperature room is about 22 C. So in this case, actually probably feeling just a little bit on the warm side. The front and rear passengers, however, are significantly cooler, noticing that they're both somewhere between the 5 and 10 degrees Celsius range. That is a very significant difference, and intuitively we know that that's going to be much cooler than the 22 degree standard room, so we can infer that they're going to be a bit on the cold side. If we switch over to a physiologic-based sensation model, in this case, looking at the Berkeley sensation model, this allows us to then make predictions about the sensation being either very warm, very cold, or somewhere in between. This is done by relating the physiologic state of the human, looking at things like the skin temperature, the core temperature, and then the derivative of skin temperature and core temperature. What you'll notice is that this tells a very different story than the equivalent homogeneous temperature. You'll notice that the driver shows a positive trend, and overall they would track closely, although of very different magnitude. You'll see that they initially start very cold in the -10 degree environment, and then as the cabin warms up, we start to see that the sensation climbs fairly steadily until they reach a near neutral sensation. The front passenger is similar, except that initially when they get into the bus, they're very cold, and when the heater kicks on, that initial wave of warm air feels very warm, but over time that starts to drop off and they start to feel cooler and cooler, but they do finish at roughly a neutral sensation. The rear passenger, on the other end, feels that same initial warmness, but over time gets much cooler, much quicker. So that passenger is actually feeling very cold at this particular, or at the end of the cycle. If we switch over to thermal comfort, which tells us how good or bad the sensation feels, and this is strictly a function of the previously mentioned sensation, we can make a determination about whether or not the bus is comfortable or uncomfortable given its current HVAC configuration. What you'll notice is that the driver was previously feeling fairly neutral, and he had a high EHT value, is now showing that as we approach the end of the cycle, is showing up positive comfort, meaning that they're feeling just comfortable. The passengers, on the other hand, are actually feeling quite uncomfortable. You'll notice that in the beginning, as things start to warm up, that initially warm sensation leaves them feeling fairly comfortable. But after sitting on the bus for 20 minutes or more, they actually shift and start becoming very uncomfortable, noticing that the rear passenger is feeling very uncomfortable while the driver's feeling fairly comfortable and the front passenger is somewhere in between the two. Looking more at the energy-based results, you can see here the cabin air temperatures are slightly different, and this is a function of the indirect heating model is controlling the air inlet temperature to a lower value because we can use that to reduce the total energy. The system that uses the local heaters is controlled to have the lower air inlet temperature. And then what we do is then supplement that with the localized heaters. The lower air inlet temperature results in lower air heater power of approximately 1 kilowatt, which is related back to the savings. The bottom left plot shows the CO2 gas cooler heating power, noticing that it's lower in the supplement or the indirect heating case. And then the bottom right plot shows the local temperature, the bottom right plot shows the CO2 entering the supercritical region. And then finally, the animation on the far right shows the three-dimensional distribution of cabin air temperatures as a function of time. Looking at these in a more related way, we can actually see that the heat pump system can be used to reduce the energy requirements of the bus, which can then be used to extend the range of the vehicle. But if we look at things like the driver comfort, the front passenger comfort, and the rear passenger comfort, we're not seeing very significant differences in the overall rating of the cabin. And what that tells us is that we can successfully integrate a lower energy consuming system without impacting the perceived comfort of the bus. What remains to be seen is how we can then modify this system to not only reduce the total energy consumption, but then improve the correlation or the comfort ratings of the system. So in conclusions, the emissions management is a driving factor in the electrification. Commercial vehicles are just one important factor of that. Most notably, to reach the Paris Climate Agreement requirements, there's going to be very dramatic changes on the horizon in terms of vehicle electrification and the amount of CO2 that can be emitted. Integrated system modeling provides unprecedented insights into the system performance, and it offers this with a very rapid, low cost, and accurate design exploration ability. And then it helps you link design targets, something like vehicle range, with the design requirements, something like the occupant comfort. And then the coupled GT-SUITE and TAITherm simulation offers an optimal simulation time for various modeling fidelities, most notably allowing you to link all of your subsystems with accurate thermal sensation and thermal comfort predictions and accurate vehicle geometry and wall temperature predictions back to all the vehicle systems that dictate the energy usage and range. And then finally, heat pumps can be used to reduce the energy consumption while maintaining the occupant perception. And what you'll notice is that that energy can be used to extend the vehicle range with no negative impacts on the occupant comfort. With that, I'd like to open up the floor for any questions that you have.
All right, thanks, John. We do have one here. So regarding thermal sensation, a few slides back, is this method 1 or method 2 sensation?
In this case, we're using method 1 sensation, but that's a fairly easy thing to change, if you're familiar with the setup.
Okay. Could heated seats be modeled with this approach?
Yep, you can definitely integrate localized heating and cooling attributes. You would do that in kind of the same way you would with any other TAITherm model, either relating that back to a heat flux or imposing a heat rate or temperature on the mannequins. It'd be a fairly standard modeling approach. We actually see that being done frequently in consumer vehicle modeling.
Okay. How would this method be extended to something like glass properties?
Fairly easily. What you would end up doing is basically changing the material assignment in the underlying TAITherm model. So it'd be minimal changes to the modeling, be a few mouse clicks overall, just selecting your new glass properties. What I'd recommend in that case is you would probably run your baseline glass properties through this cycle, and then probably set up a parametric study in GT to create the next glass property and run the following simulation.
Maybe, John, I would add to this that we have actually done a study like this. In this case, it was on a passenger car, but we will present it in about 2 weeks on a conference here in Germany. So when that will be out, you can feel free to reach us, and we can share the results of that study.
Great.
Okay. How did you account for opening doors on the bus?
Mark, do you want to take that one, or do you want me to?
I can take that one. In this case, we haven't really included the door opening of the bus in this simulation. However, we can, for example, include it in those pre-defined CFD flow fields that I was talking about before. And since we can dynamically change between them for different operations, I was talking about the blower speed and maybe the venting configurations. This can be extended also to the door opening.
Okay. Did you run the model to determine energy to reach comfort for both front and rear passengers?
Maybe I can comment on that. We have not done this exact comparison, but the results are available. So this is just kind of a post-processing step that we could do and get the results.
All right. How is solar load considered, and in which model is it considered?
So in this example, there was no solar load being applied. You would be able to consider it by using the TAITherm natural weather configuration. And that would be kind of the same way as any other TAITherm model, in that you could set it up to model a test chamber. You could set it up to do true natural weather, and then it would take into consideration anything like the vehicle motion and the different positioning of the sun as a function of time, or the direction changes of the vehicle.
Yeah, since we were concentrating on the winter scenario, we were looking at the worst case in this case, so having no solar load in winter.
All right, well, looks like that's it for questions. That will complete today's webinar. We appreciate you all attending. You will receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thank you very much and have a nice day.